So now we want to consider the application of continuous interest. So with continuous interest, we're going to let A of t be the amount in our account after t years, and R is going to be our interest rate, and it's got to be as a decimal. And if that's the case, then our population is really the population of money, okay? And it's going to be A0, which is the principal that we originally invested, times e to the RT. So this is called continuous interest because it involves the exponential. So let's consider an example here. So let's say that we have $2,500 that we started with. We invested it at 7.5% APR, and it's compounded continuously, and that tells you that we know we're using this formula. For 60 years, we want to know what's the account balance. Well, that's going to be the amount. So how do we do this? Well, start with what we know. So we know that A of t is A0 e to the RT, and A0, that was our time zero amount. So this is A0, and it's invested at 7.5%. That's telling us that R equals 0.075. Okay, so my R right here is 0.075. So we've got our equation. And then we want to know what's the amount after 60 years. So that's just asking what happens when t equals 60. So you take t and plug in for, 60 and plug in for t. So 2,500 e to the 0.075 times 60. And if you compute that, you get 225,042.83. Whoa, how about that? So you start with $2,500 and you can have $225,000 if you just leave it alone. And this is the power of continuous interest. It's exponential growth. So this grows actually very, very fast. So now we might want to know what amount would we need to get to a certain goal. So say you're saving for retirement. And for example, how much would be needed to reach $1 million in 40 years? So 40 years is your time spent working. $1 million is really not quite enough for you guys to retire because the rule of thumb is that you can draw 5% a year or 4% a year. So that's actually $40,000 to $50,000 on $1 million. And if you think about 40 years from now, that's going to be about $20,000 in today's money. That's not very much. So you have to consider interest in the equation too. So if we want the amount needed to reach a future goal, we're asking what's the start amount if we know the end amount. So we know the A of t, and we want the A0. We want the start amount. So what we want to do is take this equation and solve it for A0. So what we would do is divide both sides here by e to the RT. And on the right they cancel, and we get A0 is A of t e to the RT. Well, e to the RT on the bottom is e to the negative RT on the top. So this is the amount A0 that's needed to reach amount A of t. So what do we know? Well, we know that after 40 years, we've got $1 million. So this is actually the amount at time 40. And we also know that our interest rate is 7%, so R is 0.07. So we can plug that stuff in here. So A of 40 is 1 million, and we want A0. So our A0 is going to be A of 40 times e to the negative 0.07 times 40. So I plug the 40 in here and here. And we know A of 40 is 1 million. So this is actually 1 million times our e to the negative. That's actually negative 2.8. And if you plug this in the calculator, you get 60,810. So if you had $60,000 now, you put it in an account and just left it alone for 40 years, no more contributions, you'd still have $1 million when you retire. So that's pretty cool. So let's see how this grows graphically here. Yeah, that's a wow. That is a wow. So it's growing exponentially. Let's look at the graphs here. So T on the horizontal versus amount on the vertical. And this is going to be an exponential. It's going to start out down here at A0, which that's actually our 60,810. So that's a 1 point there. And then it's going to grow. And out here at time 40, it's up at $1 million. Okay, so the longer you leave the money in, the faster it grows. So when you get into the steep part of the exponential curve, that's when you're earning a lot of money, and that's where you want to get as quick as you can. And it comes by starting early. So you want to start to save early for retirement. And one last question to help you out with the homework here. So we might want to know what is the effective annual rate of interest. So that's the rate that includes compounding. So 7 is the annual percentage rate. That's what we call the nominal rate. So, but this is saying the effective annual rate is saying if you start with $1, how much interest do you earn in 1 year on this curve? So we're going to start, here is time 0 here, and we're going to go out to time 1. So we're going to go up and over and find that amount and how much of that is interest. So here's how you tackle that. So we know that the amount at time 0 is what we started with, the 1 million, but let's simplify it here. Let's make it $1, and then we'll see how much interest you earn on $1. So then the amount at time 1, A of 1, is actually going to be our A0, which is 1, times e to the RT, so e to the 0.07 times 1. And so this is just e to the 0.07. And if you plug that into the calculator, you will get 1.0725. So you got your $1 you started with, and you got 7.25 cents in interest. So this is our interest rate right here, 0.0725. So that means 7.25% to 2 decimal places. All right, so you should be able to try the next homework problem.